Chapter 2. The universe is not homogeneous.
Cosmology has been established on the belief that the universe is homogeneous and isotropic on large scales. Although this is a quite vague notion, it is largely accepted that, when put on sound mathematical grounds, the cosmological principle is equivalent to demanding the space-time to be of the FLRW type, named after their precursors, Friedmann, Lemaitre, Robertson, Walker. It's a framework around which the standard model of cosmology is built. Nonetheless, the recent observational data have been testing the limits of this theory, and their tenets were put under intense scrutiny after the discovery of many tensions.
The central claims of modern cosmology fail to meet the rigor that is typically required by science, especially for a field in physics and mathematics. Homogeneity is a word that should never be used to describe mass density or any other property with scale dependence. The definition of homogeneity is the same at all places. And density is rho equals mass divided by volume. While it is possible to create a nearly homogeneous object of the same atomic element, there is a limit to the size of that object because gravitational pressures eventually overcome the chemical bonds and compress the object into layers of varying density. The attractive nature of gravity gives rise to a natural hierarchical structure throughout the entire cosmos. Mass organizes itself into stars, galaxies, clusters, superclusters, and filaments. While structures within each class share similar average densities, no amount of disclaimers can make them all homogeneous across all scales. This hierarchy is fundamental. Density systematically decreases as we move from smaller to larger scales. This pattern is not a coincidence. It stems from the mathematical definition of rho, density, and the geometry of relativity. Cosmologists retreat to the notion of statistical homogeneity beyond specific scales, around 100 megaparsecs. But this idea is misleading. It tacitly admits that mass density is a scale-dependent quantity, while pretending that this dependence can be erased through averaging. The range of all possible density profiles. Consider the density for all possible objects having a radius equal to their Schwarzschild radius. In other words, all possible black holes. Typically, the Schwarzschild radius is determined from the total mass. Yet, we can also rearrange the equation and solve for the density. From this, we obtain the maximum density for any given volume, capping that density for all objects in the observable universe. We can map all possible distribution profiles alongside the Schwarzschild profile. Take a look at the figure on your screen. The red line represents the upper bound to all distribution profiles. The lower bound is the density profile 1 over r cubed. This scaling emerges because as we consider larger spherical volumes of radius r, the enclosed mass remains the same, but the volume scales according to r cubed. The green line represents a 1 over r squared decline and never crosses the Schwarzschild line. This gives us a starting point for replacing homogeneity with a realistic profile. We will go into more detail in the next chapters. A meeting of cosmologists was recently held at London's Royal Society to discuss this exact problem. Researchers presented a range of observations, including directional differences in the rate of expansion, unusual cosmic flows, and ultra-large structures like the giant arc and big ring. Don't get your hopes up. Many of the guests claim that the reported irregularities have not reached a level of significance that would justify theoretical changes. While the meeting did not produce a consensus, it did reflect a rare willingness to reassess the foundational ideas, which is a step in the right direction. In hindsight, it will be difficult to understand how we got this so wrong. The universe is neither homogeneous or inhomogeneous. These terms are not appropriate for all scales. Isotropy, on the other hand, is precisely what we're talking about when we're attempting to define a cosmological principle. Maybe not exactly, but it is very close. Statistical isotropy is the condition that the universe looks the same in all directions. Homogeneity is not something that can be observed, whereas isotropy is an observational fact in our universe. Anyone can pick up a telescope and look outward. Our solar system and galaxy are chaotic, yet the view appears relatively consistent in all directions after that. This does not mean it's homogeneous. I'm not even sure what that would mean if it was true. It's unimaginable because it is impossible. Homogeneity is an idealized descriptive term that does a bad job of translating the physical universe. It is common in the field for some to claim that the universe tends towards homogeneity as the scale increases. And I get what they're saying, it's just not true. Mass density continuously decreases as you choose increasingly larger volumes. This trend continues forever and ever, but the density never reaches zero. There is no avoiding that. Not unless you want to violate the cosmological principle, or at least the intended spirit of the cosmological principle. There's a lot of people that agree with me, and those who disagree would come around after a bit of arm twisting. One of the significant impediments to understanding comes from the way humans perceive galaxies in the modern era, particularly among cosmologists and astronomers. Humans tend to assign a special scale to galaxies, treating them as the building blocks of the universe. Galaxies only represent a single scale. We didn't even know galaxies existed 100 years ago. Einstein wrote all of relativity while thinking the Milky Way was the entire universe. As larger and larger volumes of space are considered, a natural hierarchy arises. Galaxies merge into larger structures. The same scale transition occurs from atoms to stars, from stars to galaxies, from galaxies to clusters, from clusters to superclusters, and so on.
The deduction of spatial homogeneity follows not directly from astronomical data, but because we add to the observations a philosophical principle that is plausible but untestable.
The truth is that homogeneity is indefensible because it is impossible. Earlier I said that the universe is not inhomogeneous either, and I stand by that. But only because there are multiple meanings to these words. An inhomogeneous universe might be arranged like a galaxy or a lopsided cloud. That is what people typically mean by inhomogeneous. Namely, that there is more material in some regions than there is in others. However, we can also view the universe as a collection of objects, as a single object made of different regions. In that case, the universe can be considered the most inhomogeneous thing in existence. That is because there is an incredible amount of diversity in the parameters of various regions. Solutions like the FLRW metric and Einstein's static universe begin with specific assumptions about the nature of space-time. These assumptions simplify Einstein's field equations by reducing the number of independent components in the metric tensor. The FLRW metric assumes a specific form for the line element with a scale factor A-T that depends only on time and chooses a particular spatial geometry, flat, spherical, or hyperbolic. Similarly, Einstein's static universe assumed a perfect uniform static distribution of matter with a cosmological constant chosen to balance gravitational attraction. These assumptive solutions help by making mathematics solvable. The EFE is a system of 10 coupled nonlinear partial differential equations, and without symmetry would be nearly impossible to solve. These assumptions act as boundary conditions that constrain the solution space, but complicate the interpretations. Null geodesics represent the actual paths that light rays follow through curved spacetime. They are determined by the geodesic equation, which requires only the metric tensor and its derivatives. A null geodesic satisfies the condition that the tangent vector has zero magnitude, ds squared equals 0, meaning it follows the straightest possible path through spacetime while traveling at the speed of light. Cosmological modeling is intended to describe the evolution of the largest scales, whereas null geodesics govern which aspects of that evolution are measurable. This approach is more empirically grounded because we can actually observe light rays and the paths they take. When we see gravitational lensing, redshift, or time delays, we are directly observing the consequences of null geodesics in curved spacetime. The geodesic equation is agnostic about the global structure and treats the entire metric locally. The fundamental difference is one of scope and methodology. Assumptive modeling provides global solutions that describe entire cosmological gravitational systems, but these solutions are only as valid as their underlying assumptions. The FLRW metric works well for describing large-scale universe, but breaks down near massive objects or at very early times when the assumptions of homogeneity and isotropy fail. Null geodesics provide local, assumption-free descriptions of how light actually behaves in whatever geometry exists. Birkhoff's theorem tells us that any spherically symmetric solution must be static or equivalent to the Schwarzschild metric. We can extend this theorem to all null geodesics, but we must establish a few ground rules first. First and foremost, there is no such thing as an enclosed mass in general relativity. All objects extend to infinity. In addition, we don't have perfect spherical symmetry on all scales. Instead, there is an effective gravitational center that emerges from the local interaction between a photon's path and the metric, regardless of the symmetry. In essence, each null geodesic experiences a locally defined gravitational environment that acts as if it has some effective center of gravity, even in situations that lack perfect symmetry. The photon is unaware of the global distribution of matter and only responds to the local curvature. In quantum decoherence, the act of measurement causes the quantum system to choose a definite state from a superposition. Similarly, if we observe a photon, we're forcing the space-time geometry to select a definite gravitational center from what might otherwise be more ambiguous or a distributed gravitational field. The measurement process itself becomes part of the defining effective metric that the photon experiences. Until observation, the photon's pass through curved spacetime can be thought of as sampling all possible gravitational configurations. Still, the final observed frequency reflects the definite path shaped by the effective gravitational field. Spacetime geometry has a measurement problem analogous to that in quantum mechanics. The global metric exists, in a sense, as a superposition of local gravitational effects. But the act of detecting a photon collapses this into a specific, realized path with one particular effective gravitational center, which is why Birkhoff's theorem is related here. Every observation resides within a symmetrical spacetime, but observations occurring over short distances occur below the sampling size needed for that symmetry. The frequency of a photon cannot encode all of the positions and parameters of all objects in the universe. It does, however, encode the effective gravitational center of the universe as experienced along that particular null geodesic pathway. This is a good time to address a common objection. Some argue that my profile is ill-posed and that rho of r and m of r are incompatible, and that one must integrate a local density to recover this mass. That's not the program here. We're not modeling the microphysics of a fluid or the stress energy of a localized medium. We work only with the null geodesics and the geometry they probe. The integral construction is a modeling choice. It is useful when one wishes to start from a continuum of matter, but it is not required when observations already constrain m of r directly. Integrating an assumed density to reconstruct the same m of r adds no information. Density depends on the scale you're looking at. We can define the effective density that averages over a spherical region. Rho of r equals 3 times the mass of r divided by 4 times pi r cubed. This quantity varies with radius r and gives us a way to characterize the structure that connects directly to what we observe. This is the rho of r I'm working with here. It is a scale-dependent measurement that comes from the enclosed mass, not some idealized point-by-point density field. Now, if you want to work with traditional continuum description later on, you can always recover the local density field by taking the derivative. Once you have this, the Einstein field equations will tell you what the corresponding pressure should be for whatever metric you're using. And sure, you can go down that pathway if you need to, but it's really just an accounting exercise, not something that you have to do from the start. I drew some pictures for y'all. These will serve as a good break and allow you to soak it all in visually. Because gravity binds all structures together, every star, galaxy, cluster, and filament is like a Matryoshka doll, nested within a larger and larger structure that together form the single cosmic object we call the universe. When we observe something distant, we are opening these dolls one by one and seeing not just a galaxy or a cluster in isolation, but the entire stretch of structure between us and it. The deeper we look, the more layers of the universe are contained in that view. The cosmological redshift is simply the imprint of this nesting. The light climbing out through successive layers of gravitational potential, with each layer adding to the shift that we measure.